Welcome back to Basic Electronics. In the last lecture, we obtained analytic expressions for the capacitor voltage and current for a series RC circuit with a step input voltage. We considered both charging and discharging transients. In this lecture, we will look at the graphs for these quantities and learn a lot more about these transients. We will then look at how to handle an RC or RL circuit with a piecewise constant source and follow that up with an example. Okay, let us start. These are the plots. The input voltage is given by this step waveform, the light blue curve, and the capacitor voltage is given by this curve here, the dark blue curve. And let us check whether this does correspond to the expression for the capacitor voltage that we have over here. What is V of t at t equal to 0? At t equal to 0, this term is 1, so therefore we have V0 times 1 minus 1, that is 0. So at t equal to 0, we expect V of t to be equal to 0. What about t equal to infinity? At t equal to infinity, this term is 0, and therefore we get V equal to V0, and that is what we see over here. And how long does the transient take? As we have seen earlier, the transient takes 5 time constants. Let us check whether that is happening. We have R equal to 1K, C equal to 1 microfarad. So the time constant is 1K times 1 micro, that is 1 milliseconds. So we expect the transient to last for 5 times the time constant, that is 5 milliseconds. 5 milliseconds is over here, and we observe that the transient does vanish at about that time. And thereafter, the circuit reaches a steady state, and there is no perceptible variation in either the capacitor voltage or the capacitor current beyond that point. What about the current? The current is given by this expression. At t equal to 0 plus, this term is 1, and therefore the current is V0 by R. Our V0 is 5 volts, R is 1K. So this number is 5 volts divided by 1K, or 5 milliamps. And that is what we observe over here. At 0 minus, the current is 0. At 0 plus, it is 5 milliamps. As t tends to infinity, this term goes to 0, and therefore the current is expected to go to 0. And that is indeed what we observe over here. Alright, let us now make a few observations. First, the capacitor voltage is continuous, and that is of course expected, as we explained earlier, because if there was a discontinuity in the capacitor voltage, that would lead to very large currents, which would not satisfy our circuit equations. On the other hand, there is no such restriction on the capacitor current, and we do observe a discontinuity at t equal to 0. Second observation, the capacitor current is always positive, as is also obvious from this equation. This term e raised to minus t by tau is always positive, and V0 and R are positive constants, and therefore the capacitor current is always positive. Now, since the capacitor current is C dV by dt, a positive capacitor current means a positive dV dt, and therefore we expect the capacitor voltage to always keep rising like that. Eventually, of course, the capacitor current becomes 0, and therefore the capacitor voltage becomes constant. If the current is 0, that means dV dt is 0, that means V becomes a constant, as seen over here in this graph. Since the current is large in the beginning, we have a larger slope dV dt here. Now the current goes on decreasing, so the slope also goes on decreasing, and eventually of course the current becomes 0 and the slope becomes 0. That means V becomes constant. Finally, notice that the shape of V of t or I of t is one of the two shapes we saw earlier in the graph of f of t equal to a e raised to minus t by tau plus b. If you don't remember that, you can go back a few slides and make sure that these two shapes indeed follow what we predicted in that slide over there. Okay, let us now look at the discharging transient. This is the circuit. Vs goes from 5 volts to 0 volts at t equal to 0, and the expressions for V of t and I of t, which we derived earlier, are reproduced over here. V of t is V0 e raised to minus t by tau. I of t is minus V0 by R e raised to minus t by tau. Here are the plots. This is our source voltage Vs. It starts at 5 volts. It has been 5 volts for a long time, and then at t equal to 0 it abruptly changes to 0 and then remains 0 thereafter. This dark blue curve is the capacitor voltage as a function of time, and this graph here is the capacitor current. Notice that the capacitor current is negative. Let us check whether these results, the plots here, correspond to the equations that we have derived. Let us look at the capacitor voltage first. At t equal to 0, this term is 1, and therefore V of t is V0. V0 is 5 volts, and therefore the capacitor voltage is also 5 volts. As t tends to infinity, this term becomes 0, and therefore the capacitor voltage becomes 0, as seen in this graph. And how long does this take? We expect that to take 5 time constants. R is 1k here, C is 1 microfarad as in the previous case, and therefore the time constant is 1 millisecond. 5 tau is 5 milliseconds. Therefore at 5 milliseconds we expect the transient to vanish, and that is what we observe over here. V becomes constant after about 5 milliseconds. Let us look at the current plot now. Here is the expression for the current, and remember that this is valid for t greater than 0. Now at t equal to 0 plus, this exponential factor becomes 1, and we have I of t equal to minus V0 by R. V0 is 5 volts, R is 1k, and therefore we have I of t equal to minus 5 volts by 1k, that is minus 5 milliamps. And that is indeed what we observe in this graph here. As t increases, this exponential factor decreases, and therefore we expect the capacitor current to decrease in magnitude. It will of course remain negative because of this minus sign. Eventually, as t tends to infinity, this factor will become 0, and therefore the current will become 0. And that is what we observe in this graph. As t increases, the current decreases in magnitude, and eventually it becomes 0. As we would expect, the capacitor voltage is continuous, but the current is discontinuous. There is a discontinuity at t equal to 0, and this observation is similar to what we saw in the charging case. Now the capacitor current in this case is always negative. Eventually of course it becomes 0. And what does that mean? Since the capacitor current I is C dV dt, a negative current means a negative dV dt. That means the slope of the capacitor voltage versus time graph would always be negative, and that is what we observe over here. So therefore the capacitor voltage keeps decreasing. Eventually of course the current becomes 0, dV dt becomes 0, therefore the voltage becomes constant. So there is a lot to learn from graphs, and you would have heard that a picture is worth 1,000 words, and that is also true about graphs. A graph is packed with information. We only need to look for it. And there are several features that we should look for, and we should make sure that they are compatible with the analytical understanding or the equations that we have. Let us now look at the effect of the time constant on the capacitor voltage transient. First, let us consider the charging case, in which the source voltage changes from 0 volts to 5 volts abruptly at t equal to 0, and as a result the capacitor voltage also changes. It follows this equation which we have derived earlier. Now with R equal to 1k, the time constant is 1k times 1 micro, that is 1 millisecond, and in about 5 time constants, that is in 5 milliseconds, we expect the capacitor voltage transient to vanish and a steady state to be established. And that is what we observe in this plot. This light blue curve corresponds to R equal to 1k. In the beginning, the capacitor voltage has been 0 volts for a long time. At t equal to 0, it starts rising towards 5 volts. And in about 5 milliseconds, this time point here, it reaches almost 5 volts and does not change after that. Alright, now let us look at the second case, namely R equal to 100 ohms, that is 0.1 k. What is the time constant in this case? It is 0.1 k times 1 micro, that is 0.1 milliseconds. Now in this case, we expect the transient to last for 5 times 0.1 milliseconds, that is 0.5 milliseconds. And that is indeed what we observe in this plot. This is 1 millisecond, 0.5 millisecond is somewhere here, and we observe that for R equal to 100 ohms, we reach the steady state in about 0.5 milliseconds, and after that point the capacitor voltage does not change. Let us now consider the discharging case. So Vs changes from 5 volts to 0 volts at t equal to 0, and as a result the capacitor voltage also changes, and it follows this equation which we have derived earlier. Now with R equal to 1k, the time constant is 1 millisecond, and in about 5 time constants the transient vanishes as seen in this graph. This is 5 volts, and at t equal to 5 milliseconds we reach steady state and the capacitor voltage does not change thereafter. For R equal to 100 ohms, the time constant is 0.1 millisecond, and in 5 tau, that is in 0.5 milliseconds, we reach steady state here and the capacitor voltage becomes constant. So far we have considered RC and RL circuits with a constant source, a voltage source or a current source. Let us now look at RC and RL circuits with a piecewise constant source. Here is an example. There is a voltage source here which varies with time, like that. In this interval, t less than t1, this voltage is 0. Between t1 and t2, it is non-zero, let's say 5 volts, and then for t greater than t2, it is 0 again. Let us see how we can handle such a situation. Clearly this is not a DC source or a constant source, but it is piecewise constant. We have one piece here which is constant, we have another piece here which is constant, and we have a third piece here which is constant. And in each of these intervals we can use the expressions that we have derived, that is For any current or voltage x of t in the circuit, we can write a general expression such as x of t equal to a1 e raised to minus t by tau plus b1 for the first piece, that is t less than t1. Similarly, for the second interval from t1 to t2, we can write x of t as a2 e raised to minus t by tau plus b2. Now these a2 and b2 are also constants, and generally they would be different from a1 and b1. And finally, in this third interval, that is t greater than t2, we can write x of t as a3 e raised to minus t by tau plus b3. In order to get a complete picture, what we need to do next is to find this tau, the circuit time constant, and also these constants a1, b1, a2, b2, etc. Now the time constant is given by R times C for an RC circuit, where R is the Thevenin resistance seen by the capacitor. For an RL circuit, tau is given by L divided by R, where R is the Thevenin resistance seen by the inductor. We have already seen these formulas earlier. How do we obtain these constants? A1, B1, A2, B2, and so on. What we need to do is to work out suitable conditions on x of t, which could be a current or a voltage, at specific time points. For example, in this case, we might look at x of t at t1, t2, minus infinity, and plus infinity. And in order to do that, in order to find these conditions, we can use the following considerations. A, if the source voltage or current has not changed for a long time, long compared to the circuit time constant tau, then we know that all derivatives must be 0, because all quantities in the circuit, all voltages and currents, must have become constant. The circuit must be in a steady state. For example, take this piece. If Vs has been 0 for a long time, then we know that when we come to T1 minus, that is just a little bit before T1, then the circuit is in steady state and all voltages and currents must be constant. And once we know that the capacitor current, which is given by C dV C dt, must be equal to 0. So the capacitor can be treated as an open circuit, and the inductor voltage, which is given by L dIL dt, must also be 0, because IL would have become constant. That means the inductor can be replaced with a short circuit, since the voltage across the inductor is 0. B, when a source voltage or current changes, say at t equal to t0, in this example t0 would be t1 or t2, then the capacitor voltage or the inductor current cannot change abruptly, as we have seen earlier. That means Vc at t0 plus, the capacitor voltage at t0 plus, must be equal to Vc at t0 minus, and in an RL circuit, the inductor current IL at t0 plus must be equal to the inductor current at t0 minus. So using these considerations, we can work out suitable conditions on the current or voltage at specific time points, and then use those to compute these constants A1, B1, A2, B2, and A3, B3 in this example. So once we have tau and once we have these constants, we have a complete description for the quantity of interest. Let us now apply the ideas that we have just learned in the last slide to this particular example. We have an RL circuit here with two resistors, R1 and R2, and a single inductor. R1 is 10 ohms, R2 is 40 ohms, and the inductance is 0.8 Henry. The input voltage is a pulse given by this graph here. T0 is 0 and T1 is 0.1 second. Up to T0, the source voltage Vs is 0 volts. Between T0 and T1, it is 10 volts, and after T1, it is again 0 volts. And we are interested in finding this current through the inductor as a function of time. Step number 1 is to identify intervals in which the input voltage is constant. And from this graph, we can see that there are 3 such intervals. Interval 1, t less than t0, where Vs is 0 volts. Interval 2, t0 less than t1, in which Vs is 10 volts. And interval 3, that is t greater than t1, in which Vs is 0 volts. Like we mentioned in the last slide, what we need to do next is to consider each of these intervals, identify the circuit time constant in each interval, write a general expression for I of t in each of these intervals, and then find suitable conditions on I of t at suitable time points, which will enable us to calculate the coefficients, the constants involved in those expressions. So let us begin with the circuit time constant. Now we figure that in all of these intervals, the time constant does not change because the circuit topology is the same in all 3 cases. So let us proceed with that calculation now. What is the circuit time constant tau? It is L by RTh, where RTh is the Thevenin resistance as seen by the inductor. To make this calculation a little easier, let us redraw the circuit as shown here. What we have done is we have taken this inductor on the other side. That of course does not change the circuit. And now we look at the rest of the circuit, this circuit here, from the inductor. And note that the circuit topology is the same in all 3 intervals. The only thing that is changing is the value of Vs. In the first interval, Vs is 0. In the second interval, it is 10. And in the third interval, it is 0. So the Thevenin resistance seen by the inductor is the same in all 3 cases. And how do we find that? We deactivate the voltage source. That means we short this voltage source. And then what happens is R1 and R2 come in parallel. So therefore RTh is simply R1 parallel R2. So that turns out to be 10 parallel 40 or 8 ohms. Then the time constant is given by L divided by RTh. Our L is 0.8 Henry, RTh is 8 ohms. So therefore the time constant is 0.1 second. Next, let us find suitable conditions on I of t, which will eventually enable us to find the constants involved in the expressions for I of t in these 3 intervals. Let us consider t0 minus, that means just before t0. What is the situation at t equal to t0 minus? The source voltage has been 0 for a long time. We have a steady state. All currents and voltages have become constants, and therefore this V, which is L di by dt, is 0. If V is 0, the voltage across R2 is 0. That means no current can flow through R2. So the current path that we have is like this. And since this voltage drop is 0, the current I must be Vs divided by R1. Now Vs is 0 in this interval up to t0 minus, and therefore the current I at t0 minus must be 0, like that. Now since this I is an inductor current, we know that it must be continuous. That means I at t0 plus must be equal to I at t0 minus, and therefore we get I at t0 plus equal to 0 ampere. Alright, let us now obtain another condition on the current, and we will do that by assuming that this Vs did not change. In real life, of course, Vs has changed at t1, but let us pretend that it has remained constant. The question is, does this make sense? How can we assume that Vs is 10 volts in this interval when it is actually 0 volts? The answer to that question is that it does make sense as long as we are in this region up to t1. So what we will do is we will assume this condition, but we will consider the solution to be valid only up to this point t1. To put it a bit informally, the inductor or the circuit does not really know that a change is going to take place at this point, and therefore the response of the circuit would be the same in this interval whether or not Vs stayed constant or it went back to 0 at this point. Okay, with this situation, let us now find this current as t tends to infinity. What do we have at t equal to infinity? The circuit would have reached steady state. All currents and voltages would have become constant. Therefore, this V, which is L di dt, would have become 0. So we have a short circuit here, and the current I would then be Vs divided by R1. The current through R2 of course would be 0 because this voltage drop is 0. At t equal to infinity, Vs would be 10 volts. So therefore the current I would be 10 divided by R1, that is 10 volts divided by 10 ohms, that is 1 ampere. Let us now use these two conditions, namely I at t0 plus and I at infinity, to obtain the solution for I of t in this interval, and we will do that in the next slide. In conclusion, we have started looking at RC and RL circuits with a piecewise constant source. In the next lecture, we will continue with the RL circuit example and obtain the complete solution. Until then, goodbye.